Okay, so today we will move to another new algorithm. So it's still regarding classification, but what today we will mainly focus is unsupervised. So all the algorithms that we discussed before are supervised. So for supervised learning, we have features, and we also have targets, the target values, okay? And they are already tagged for the target value for the, especially for classification, okay? For unsupervised learning, we don't have, so no tagged targets. Okay, so that's why it's called unsupervised. And the first approach that we will learn is KNN. So that's what we will learn today. It's K nearest neighbors. So let's take a look at the concepts of K nearest neighbors. Okay. So just keep this in mind. This is regarding unsupervised learning. Okay. So the first one we will learn is KNN. So it's K nearest neighbors. Okay. And yes, as KN is a typical example of lazy learner. Okay. It doesn't learn discriminative function. Not like if you recall previously, is that we have cost function. So it doesn't learn a discrete function from the learning, from the training data. Is it so? Previously we have cost function, as we try to minimize the cost function, and then try to get to the optimal weights. So that's the goal, is it? And of course for decision tree. For the decision tree is as we try to we have that impurity, is it? And we try to have the maximize the gain. Okay. But anyway, for KNN, it doesn't learn discriminative function from the training data, but rather it memorizes the training data set. Okay, and if you recall previously, it doesn't involve memorize, is it? So that's the big difference here. That's why we call it unsupervised. And regarding unsupervised learning generally, so clustering and underclass there are a couple of different approaches. Okay, KNN is well like the clustering, and neural network. It also has some of the approaches that's also support unsupervised learning. Okay, and like the GAN. Okay, so but what this section and a couple of later sections that we will discuss focus on clustering. Okay, and later on when we do neural network and deep learning, we will see if we have time to cover this. Okay. So that's K nearest neighbor. So K nearest neighbors, KN, the basic idea is, so here there are two parameters important. Okay, one is the number of neighbors this is regarding neighbors. K is number of neighbors. And of course, when you said neighbor, then you needed to have some distance to measure the neighbor, is it? So how far away you consider, you define as neighbors, is it? So these two parameter are key point for KNN, number of neighbors and the distance. Then the goal is algorithm to find the K nearest neighbors of the sample that we want to classify. Then you assign the class label by majority vote, okay? And the last time when we discussed random forest, so we also kind of get the concept about majority vote, okay? So, okay, nearest neighbor, so here is a diagram showing, okay? So in this case is, so we have the numbers, is it? So in this case, the K is 5. Okay, K is 5 nearest neighbor, okay? And as to distance later on, we will see. So assuming here the distance, we can kind of visually see it. Is it? Anyway, it's two-dimensional, so it's, so based on the mass, then we know how to find the distance, okay? So then in this case, so this is a point, is it? A new data point. And as a new data point, how you are going to assign it to the class, is it? So you have, so in this case, we have 3 classes. We have cross, we have circle, and we have triangle, is it? So how are you going to predict what the class it is it? So the idea then is you choose the 5, in this case, K is 5, so K, 5 nearest neighbor, as it? So clearly in this diagram shows within this circle, 5 nearest neighbor. And among this 5 nearest neighbor, what are the majority class it is it? Then definitely clearly we can see the triangle, we have 3 and the other just have 1. So this is majority vote. If this is majority vote, and then you will just consider, okay, you predict it also as triangle, okay? So this is the KNN idea. So it's kind of, you know, straightforward, is it? Pretty obvious. Okay, then let's see the KNN. Then you just think about for every new data, is it? You need to do that kind of neighboring and the majority vote, is it? So it says the advantage of such, so it is a memory-based approach, is it? Because you needed to find the K neighbors, is it? So the advantage is it can adapt pretty fast when it gets the new training data. Okay, so that's its advantage. But of course, the downside is also because of the memory based. Okay, so the computation complexity, is it, for classifying new samples also grow linear with the number of samples in the training data set, is it? So if you have a very large number of samples in the training data set, then the computation we can clearly see is that it's much higher, okay? And also the other downside is it cannot discard the training samples, is it? Because you're going to consider the neighbors, is it? So you need to have all of the data be in the memory, as it? So storage space can become challenging when we work with large data set. Okay, so the memory base has some advantage, but it also has a disadvantage when the data size is large. So that's the upside and downside for KNN. And also, like previously we said, that so the number of neighbor, the right choice, then is very critical to find a balance between overfitting and underfitting. That because if you choose the K is too small, that then maybe it can lead to overfitting. And if you choose it too large, then it may lead to underfitting. So we need to find a balance. And also the distance metric. Okay, that's also important. And usually is that it uses simple Euclidean distance, okay, for real value samples. But it also supports others, it's not just this one, okay. And if we use Euclidean distance, then we also need to standardize the data, okay, because the feature contribute equally to the distance, is it? And if you recall decision tree, and of course the random forest, is it? And in that learning, we don't need so no data scaling is needed, is it? Because that's based on each of the node decision, okay. Okay, then regarding the distance, that so distance, we said the Minkowski, okay. So this distance is generalization of the Euclidean and Manhattan distance. Okay, we're quite familiar with Euclidean distance, is it? So if in the 2D, is it? Then in math, we already learned the Euclidean distance and the Manhattan distance. So Euclidean distance, then in this case, the P is 2. Okay, P is 2. And in Manhattan distance, then P is 1. Okay, so basically it's just, this is Manhattan distance, okay, absolute offset between those two. But be careful, okay, this is regarding vector, okay, vector. And other distance metrics also available in sklearn, okay? And if you're interested, then you can go ahead and look at the official document about the distance metric. So this is regarding the distance. Okay, and then what next try to discuss is about like the overfitting. Is that KNS is very susceptible to overfitting. It's because of it's called curse of dimensionality. Okay, so just keep in mind this term, curse of dimensionality. What is this? This describes a situation that a feature space becomes increasingly sparse. Okay, is that for an increasing number of dimensions, but your training data set is fixed size. Okay, but the feature space is quite large, is it? So it becomes increasingly sparse. Then it says like the situation is just like even the closest neighbor can be too far away in high dimensional space, okay, to give a good estimate. So this is called curse of dimensionality, okay. Curse of dimensionality, if you recall in decision tree, we also said decision tree can also give you like a feature importance. That you can pick the feature importance, the examples. And for the feature importance, then it's kind of, you have too many features, that then you can filter out some of the features. Features not important. That's it. So this curse of dimensionality, one way that we can reduce its impact is you can filter out some non-important features, is it? And also, if you recall, in regression, we also, logistic regression, we also learned the regularization, is it? Through that parameter C, is it? Of course, this is in sklearn, is it? That L2 regularization. Is it L2 regularization is to what? Is to manually add bias term. Is it? The bias term is through what? Is through the weight. Through the weight, is it? And so this lambda is the sklearn's inverse of the parameter C, is it? And this term, if you add it, it's kind of like you add more impact for bias. So of course, then it can bring down, is it, overfitting issue, okay? So, but sometimes regularization is not applicable, is it, like a decision tree and KNN, is it? Then what we can do is we can do feature selection like we previously saw, is it? It's called feature selection, is it? And the dimensionality reduction, okay? Later on, we will also learn some other technique to do dimensionality reduction, okay? And if you recall, like for SVM, support vector machine, is it? For the nonlinear, we use the kernel trick. And for kernel trick, basically it's what is to get from low dimension to high dimension. You increase dimension, is it? You increase dimension so that we can do the hyperplane, as I find the hyperplane so that it can separate the class. And over here is we need to do dimensionality reduction, okay, to overcome the overfitting issue, okay. So it's, you can see it's based on the need, okay. So the Euclidean, we already saw that, and we already kind of know that. And one of the downside for KNN, if you recall, is a large data set, the storage will be an issue because it's in memory, is it? And one way to help around with it is parallel processing. Okay, can speed up, because if, and on the other hand, it also can be slow. Therefore, if the larger data set, is it, because you need one by one, okay? So for KNN, then we can borrow parallel processing. Parallel, if you recall, in sklearn, there is a parameter called the n jobs. Okay, so n jobs, then it's support multi-core processing, okay, simultaneous operation. So it can help at a certain point to speed up, okay. Okay, and then over here, we gave a brief comparison among all of the algorithms that we have learned so far, okay, not all of them, okay. And linear and the non-linear, we already see, is it for SVM, then we have the kernel trick, is it? And sometimes for linear, we can also borrow polynomial. and then convert it basically to linear. Is it? So that's to tackle nonlinear and the linear problem, okay? And the decision tree. And if you want to use decision tree, that's because it's attractive is what? It's interpretability. Is it because it's what? It's white box. Is it white box? We can see quite a lot of internal decision. Not like of the others, we only know the end result. We don't, we cannot see what's internal, the learning, how it functions, is it? But with decision tree, then we can know the internal, okay? And then for logistic regression, be careful, it's about classification, is it? And if you want to do the stochastic, is it? So that's because for batch processing, then you need to load all data into memory at one time. But for the stochastic, we call it an online algorithm. It's because it's one by one. Of course, it's also support mini batch, if you recall. Is it? Okay, and but with logistic regression, what it focus is probability, okay, of some classification. Is it? It's not like purely yes or no. It's the probability of yes or no. Is it? And support vector machines is that it also has a kernel tree. Is it? So they can help a lot with the non-linear ones, is it? Because of the kernel tree, okay? But of course, it has quite a number of parameters that we need to tuning, is it? If you recall the gamma parameter, is it? The gamma parameter is for the kernels, is it? Is for the kernels. So besides the C, is it? So some more parameters, then you also need to do train, okay? And ensemble method that we learned is a random forest. So it's not using a single, it uses multiple tree, is it? And then it doesn't, we don't need to worry about parameter tuning, is it? And also not overfitting, is it? So it says random forest ensemble method a lot of times quite attractive also, okay, for many practical problems, okay. And the KNN, then it's an alternative because it's a lazy learning, okay. And if you get some data and you have no clue, is it because it's not categorized well, then with KNN, then it's also quite helpful, etc. So, but it's computationally speaking, it's expensive. Okay, so that's the overall comparison among the algorithm that we have learned so far. And what the next part we want to discuss is about data pre-processing. Okay. So this is not just for KNN, it's just generally speaking, okay. The first is missing values, is it from the data set, okay. So how are we going to deal with it? If you recall previously in Python, we learned, is it like a drop NA, is it fill NA, yeah, those kind of thing to deal with missing that. But with machine learning, how are we going to handle that? Is it we just remove, or how are we going to do the imputing? The second thing is regarding categorical data. But with all machine learning, we need what? It needs numerical data. But a lot of time in the real world, what you collect is not numerical data. But if you recall previously, we learned that span prediction And for spam prediction, it involves word. Is it? And the words, definitely, there is no numeric value directly associated with it. Is it? So over there, we use some other technique. Is it? We do some mapping. Is it to match a word with some numeric number? Is it? So that's regarding categorical data. Is it? How are we going to convert them to numeric data for the algorithm to do training? The third one over here we are going to discuss is how do we select relevant features, so feature selection, okay. Feature selection, okay. So in previous discussion, we discussed like the dimensionality reduction. Reduction is the curse of the dimensionality, okay, to solve that issue. Because you may have a lot of features, is it? So how do you get rid of some noise? Okay, for missing value, is it? Missing value is that some cases it's like a blank space in the table placeholder, is it? Like a net, is it? Okay, and that's from NumPy, is it? Or like null values, is it? Sometimes that can happen in database, is it? And previously we learned like the drop NA method, fill NA method, is it? And fill NA, sometimes we can also use some technique, we use some mean value, or you fill with some value, not just drop it, is it? Because you're going to fill it with some value, okay? So later on we will see, okay? So sklearn has some package that can help us handle the imputing, okay? So that's regarding the missing value issue, okay? Like, because if you just do the drop NA, you may drop too many samples. When you drop too many samples, sometimes you may even lead to remove too many features. If you remove too many features, then it will cause a problem of underfit. Is it? So that's not ideal. Okay, then what is imputing missing value? Okay, imputing missing value is we can use different interpolation technique to estimate the missing value. Okay, so we use some interpolation technique. Okay, one of the common one is that use some mean value. Okay, mean value. Okay, and then the general idea for deal with missing value and imputing value is if you have the training and the testing data set, is it? And then we can provide some approaches to do imputing. Is it? After imputing, then you need to transform, is it? So then you have transformed training and testing. And after that, then you can start training the model, okay, and then predict the model, okay. So that's just a general flow for handling missing and imputing data. And what next is about categorical data. For categorical data, there are two different ones, nominal and ordinal, okay. Ordinal features that can be sorted, is it? Like good, better, best, something like that, is it? Or like the t-shirt size can be XL, L, and M, and small, is it something like that? And then for this ordinal, then it's logical that you give some values. Is it like if you have this map to 3, this map to 2, and this map as 1, is it? Then that's logical. But there are some other, it's called nominal feature. Nominal feature, then there is no order, is it? No order. No order like the color. For color, how do you order? Is it? Then in this case, how are we going to handle it? And if you recall in Python, we learn like the get dummy, if you recall. Is it like the dummy values? Is it? Basically, what that means is, then in this case, if we use a dummy, then we kind of increase the number of features. Because previously you just have color, this is single feature. Single feature, is it? And suppose the color you have red, you have blue, you have green, is it? Then in this case, you're going to convert it to what? Convert it to like color red, then color green, and color blue. You convert to 3 columns. Basically, it's kind of like 3 features. 3 features, is it? Then if it is red, you put as 1. And if it is not, it's 0. If it is green, then it is 1. If it is blue, it's 1. All other cases are going to be 0. Okay. So there's kind of, you increase the dimensionality. Okay, so that's for nominal features. Okay, and then what next is class label. Is it? Class label, then we also need numerical values, is it? So we can encode the class label, is it? Map of ordinal, is it? Features. And for sklearn, there is also a class called label encoder. You can directly borrow to use it, okay? So, and if you recall the previously, we mentioned the dummy for the nominal. This is for nominal, okay? For nominal, so that technique basically is called one-hot encoding. Okay, it's called one-hot encoding, okay? Label encode good for ordinal. Okay, good for ordinal. One-hot encoding, then it's good for nominal, okay? Create is a dummy feature, okay, dummy feature. So just be careful, okay, these two are different. Label encoder and one-hot encoder is different, okay, the case. So for one-hot, it's good for nominal. Okay, and this we already see quite a number of times. It's split data into training and testing data, okay. And then for standardization, that feature scaling, basically previously we also saw that, we just didn't summarize. So there are 2 common approaches, normalization and standardization. That for normalization, then it's rescaling the feature to the range between 0 and 1, okay? And we also can call it minimax scaling. So it's you use the value minus the minimum, and divide by the offset between the difference between max and the minimum, okay? So this we call normalization. And the standardization is we are going to center the feature column at a certain mean value with some standard deviation, okay? So this is about mean. This is the standard deviation. So basically, it's try to center the feature around the mean 0. To do some translation. And with, but with a certain standard deviation. Here is 1. Okay, so this is it's a try to bring the sample to normal distribution, is it? So that's what a standardization used. Okay, then over here discuss about overfitting, generally how we deal with overfitting. Is it for underfitting? Then if you have underfitting, sometimes too few samples, is it can lead to underfitting? Is it maybe the features, too few features? That may also lead to underfitting. Is it for overfitting? Is it overfitting is for training? For training, it's pretty good. It's fit pretty good. Is it? But it does not generalize well for new data. Is it? Because of high variance. Underfitting is a high bias. Is it? Okay, and the reason is that for overfitting is the model may be too complex for training data. Is it for training data? So that's why it does not generalize well. So that's why we need to reduce the generalization error. Is it? How are we going to do it? You can collect more training data. Is it? That can also help. Okay, and also introduce penalty with regularization. So this technique we already learned, is it? Because this kind of manually add bias, that its influence. And we can also choose a simple model with few parameters, is it? With few parameters. And also reduce the dimensionality of data, is it? So this regarding feature selection. Feature selection, okay. It says common way to reduce overfitting is through regularization and dimensionality reduction using feature selection, okay. So this is regarding feature selection. And then the regularization is the L2, that we already discussed, that we use the weights, that square and the sum of that, and this can penalize large individual weights. That, so this is called L2, okay. So you square of the weights. Another one is called L1 regularization. And keep this in mind, okay. L2 generally the purpose is to do regularization, to reduce overfit. Okay, and there's another one called L1 regularization. So it's just to add of the absolute value, no square. Okay, no square. And then it says L1 regularization, it will yield sparse feature vectors. It will lead quite a lot of feature weights be 0. So basically, then based on this idea, then it's good for what? For feature selection. Okay, so L1, generally speaking, it's used for feature selection. Okay, it's good for feature selection because it will generalize some feature will lead it to 0. Okay. And why we see this, we can, and if you recall in sklearn, okay, and how do we specify, then in the model, like for logistic regression, then using the argument penalty, then you specify it's L1 or L2. Okay, later on in our example, we will also see, okay. So L1 or L2, then you it depends on the penalty argument. But the real one is for the C. Is it? It's for the C. And over here to also say, if you want to increase the regularization strength, then we choose the lower value for C. They choose the lower value, okay? Then it can lead to more zero weights, etc. So enforce the sparsity. Okay, then here is a visualization view about the L2 and L1 regularization. Okay, so this part, this shaded part, describe what? Describe the L2. L2, is it in this case? And it's a circle, is it? And over here, we have the weight. This is regarding weight, is it? This is just 2D case. And if you recall, is it? If you recall, it's convex, is it, in 2-dimensional? So this is a contour. Contour, is it? And this is the lowest point. Is it lowest point? Okay, lowest point is minimize the cost. Is it? Then it's going to be here. Is it? So that's the weight, W1 and W2. Is it? If we don't consider any regularization. But if you consider regularization, then that point, the lowest point, going to be moved to this point. So the intersection of the L2 and the cost function here, is it? And then you can clearly see the weight is bringing down, is it? So both weight are bringing down. So that's why it reduces large weight impact. Okay, that's why we say it's bring it back. They bring it back. Okay, so that's regarding L2 interpretation from the mass point of view. And then for L1, similar, is it? Then L1, then we see it's linear. So that's its part for L1. Is it this this line? Is it directly line the diamond shape? Is a diamond shape? Okay, then diamond shape. Then you can clearly see here is the intersection point. Therefore, this intersection point, do you see it's bringing W1 to 0? Is it? So with L1, then it can bring some weights to 0. And if weight is to 0, so it's no influence. Is it? If it is no influence, then you can remove the feature. Because it's removed, that's why we call it a feature reduction. Okay, and you can reduce the features. Is it? So this is regarding the difference between L1 and L2. Okay, so keep that in mind. L1, when you do the feature selection, and then L2 is what? Is to do the regularization. Okay. Okay, and some alternative is you can also do some sequential feature selection algorithm. Okay, and over here we are not going to discuss it. If you're interested, you can take a look. Over here, introduce sequential backward selection. And for sklearn, it also provides some of the feature selection algorithms. And if you are interested, and you can check the official document. Okay. So it's used recursive backward elimination. Okay. And if you recall previously, we also in the decision tree and random forest that we discussed the feature importance and we can access it. Is it? So it says using L1 regularization, we can zero out that irrelevant feature via like logistic regression. Okay, so over here just that in machine learning, you're not just limited to some single algorithm. You can use like logistic, maybe do some filter out of the feature reduction, is it? And you can also use like the SBS for feature selection. Then you apply it to KNN, is it? And using random forest, we can also measure feature importance, is it? Feature importance. Okay, feature importance, if you recall, it's in sklearn, is it? It's through that feature importance attribute. Then we can directly get the idea of feature importance, okay? And later on in our example, we will also see sklearn that also implements it called select from model, okay, object. And this select from model object, it can select features based on some user-defined threshold after model fitting. Okay, this is sometimes quite useful, is it? Then we can also use random forest classify as feature selector, is it? And some intermediate step, is it? And later on, we will also learn in sklearn, we can also do pipeline way, okay, to do some pre-processing, okay, before we do the real model training. Okay, and over here, it's regarding the feature importance with random forest, is it? But over here it says if two or more, we also need to be careful as with random forest feature selection is if two or more features are highly correlated, is it? Then it says one feature may be ranked very high, while the other may be not fully captured. Okay, so sometimes you may also need to consider the highly correlated impact. Okay, so that's the idea about the feature selection. What is the next one we want to discuss? It's about cross validation, CV. A lot of time you will also see. And this normally is for parameter tuning. And previously, if you recall the data set, we split it into training and testing. Is it? If we just use training to do parameter tuning, a lot of time it won't give the highly efficient result. Okay, so that's why over here, a lot of we add another concept, we call it cross validation. Okay, cross validation is for parameter tuning, is it? So based on some of the data set, okay, then you cross validate, then you choose best parameter. With the best parameter, then for the training data, is it? You can retrain the model, okay? And then for the testing, then we do the model prediction. So that's the idea about cross validation. So it's basically just on some data set, then your purpose is to train the best parameter, okay? And in the real world, a lot of time we have the k-fold cross validation. Okay, cross validation. So what that idea is, so here you have all the data split into training data set and testing data set, is it? Then based on the training data set, we further split into multiple folds. Okay, multiple folds. And then for each of the fold, you are going to select one fold for the cross validation, and all of this as training. And try out with different parameters. Okay, you can keep doing for each of the folds. Use it as cross validation. When you try to tune the parameter, okay, try to tune the parameter, okay. So this is an idea about the cross validation, okay, and we call it the K-folds cross validation. So it's also quite straightforward, is it? Okay, so that's all of the theoretical parts. So today we didn't get a chance to go over the example. So next Monday we will take a look of the examples regarding of the concepts that today we discussed. So before we dismiss